Okay, so over here we have a sample of a compound that contains only the elements C, H, and N. Is burned completely in O2 to produce 44.0 grams of CO2, 45.0 grams of H2O, and some NO2. A possible empirical formula of this compound is, and it's all there. Now, I know this question may look a little bit intimidating at first, but here's the deal. We don't even have to worry about this thing because it says some. So there's literally nothing that we can do. Let's start with CO2. Okay, let's go. So we have 44.0. We're doing CO2. 44.0 grams of CO2. And this is grams. And since grams has to cancel with another gram, so we'll keep 1 mole over here, and that equals to the molar mass of CO2, which is also 44 grams. And that would equal to 1 mole of CO2. Excuse my writing right now. And then we are going to do H2O. For H2O, we have 45.0 grams of H2O. And then we will do the molar mass of H2O, which is 18, which would equal to 2.5 moles of H2O. Now, keeping in mind these two numbers, we will determine what is going on here. So now that we know the moles, I'll go ahead and erase it. If you really want to jot it down, you can. So we said we have 1 mole of CO2, right? We have 1 mole of CO2. So in CO2, you can notice that there's 1 carbon for every 2 oxygen, right? And if you want more clarification on it, here's a Lewis diagram. I'm not putting lone pairs anymore. I mean, not right now. So over here, you can notice that this fills the octet rule, and for every 1 C, there are 2 oxygen. That's one way to think about it. So again, 1 mole of CO2. Now in your previous classes, you've learned that, and as I said, 1 carbon is in CO2. So 1 mole of CO2 will equal 1 mole of carbon. Rewind that again if you didn't understand it. Okay, and then we're moving to H2O. We said that we have 2.5 moles of H2O. Now, mind you, we are looking for H, not H2O. And it's asking us to determine the empirical formula. So what you do is you take 2.5 moles of H2O. I already wrote it down, but I'm going to write it again. And then you will notice that we have 2 hydrogens for every oxygen. The particle diagram looks kind of like that. This is negative, positive H. Well, those positive don't look positive. So yeah, that's O and that's H. For every 2 H, there is 1 oxygen. Keeping that in mind, we can change the color right here. We can determine the number of H. So there are 2H in H2O, and over here we said they're 2.5, so we'll write that down, 2.5 H2O. And this is more like an algebraic, I can't pronounce algebraic, I can't. So yeah, there are like 2.5 moles of H2O, and there are like 2H in every H2O, no matter what. So if there are 2.5 over here, you'll simply multiply by 2.5 by 2, which will give you 5H. Now, you have 5H and 1C. I wrote that down real quick in case I forget. Now, let's move to the last part of the question. It says a possible empirical formula of this compound. So we have C's, C's not C's, C and H. We have 1 and 5. So the empirical formula would be CH5. Now, if I know you might be like, oh, but we don't have the moles or any calculations for NO2, and we can't because it says some NO2. So we can't really just assume and use the same principle that we used before, like there are only 1 carbon in CO2 and 2H2 and 2H in H2O. We cannot use the same because we don't have anything to start with. So we have CH5, and if you look towards these, you'll notice that there's only one option that contains CH5 because this contains C2, C3, C. Yeah, there's a possibility, but it doesn't have H5, so this doesn't qualify. Only this option tells us that we have the right answer because, let's see, let's cross check. C, we got that. And we have H5, and we got that, so that's the right answer.